Okay, let us start today's session. So you can see here the first thing. So what we're going to discuss, that is the previous thing that we're going to revise, like physical units, quantity, and also some part of the errors and relative error and percentage error, and also the significant figures, dimension, dimensional formula, dimensional equation, dimensional analysis. Okay. So first, the physical quantity. So these portions are actually covered, and we will be going to in a brief overview of all these things. Okay. So a quantity which is measurable is called physical quantity. And what is a fundamental quantity? A physical quantity which is the base and cannot be derived from any other quantity. Okay, that is known as fundamental quantity. Examples: length, mass, time, etc. Then what is derived quantity? Physical quantity which can be derived or expressed from the base or the fundamental quantities. That is derived quantity. Example: speed, velocity, acceleration, force, momentum, torque, energy, pressure, density, all these things. Okay. Now what is a unit? So measurement of any physical quantity involve comparison with a certain basic or arbitrary chosen internationally accepted reference standard called unit. Okay, so you have a reference, you are basically comparing with that reference, and that reference must be internationally accepted, and in with that thing you can define a unit. So here also the fundamental units, the units of the fundamental or base quantities, that is fundamental unit or base unit, like meter, kilogram, second. If you see for uh, distance, for mass, for distance, meter, mass, kilogram, time, second. Then derived unit, the units of the derived quantity which can be expressed from the base or fundamental quantities. That means from these fundamental units or fundamental quantities, whatever the units are derived, these are practically the derived units. So you know the basic things, like if you have meter per second, that is that is a unit for velocity, that is a derived unit. Kg per meter cube, all these things are coming under derived unit. Okay. Someone else can. Okay. Now, so and other things like kg meter per second square. Okay, kg meter square per second square, all the things, if you consider the unit of pressure, moment, momentum, all these things. Okay. Now system of units, a complete set of both fundamental and derived unit is known as system of units. They have certain characteristics. There are certain characteristics of standard units. A unit selected for measuring a physical quantity must fulfill following criteria, following requirements. One, it should be well defined. Then, it should be suitable. It should be of suitable size. That is, it should neither be too large nor too small in comparison to the quantity to be measured. Suppose if you are measuring, uh, let's suppose you are measuring diameter of pen or something, and if you are using a unit which is actually in kilometer, so that is not practicable, na? So you have to be practical enough. So whenever you are using a small thing, small quantity, you should take that suitable size for that. Whenever you are using to measure length of a road, then you should use kilometer, correct? So that is what this point suggests. Then it should be reproducible at all places. Then it should not change from place to place or time to time. Suppose here we are using something, okay, some standard unit, you are using kilogram or something, and in other place if you change place or country, but using some that thing, so that will not be a good thing, good practice. Okay, so unit should be universally accepted. Okay, then it should not change with the physical conditions such as temperature, pressure, etc. It should be easily accessible. So various system of units. In earlier times, we know some, like they are using FPS, MKS, CGS. Those things are used for measurement. They were named so from the fundamental units in their respective systems. Like you see FPS. So if you see these quantities here, uh, in this length and mass and time, here in FPS it is foot, pound, second. CGS it is centimeter and then gram and then second, and here it is meter, kilogram and second. Okay, now SI unit, so that is Systemi Internationale. Okay, that is SI unit. So the SI unit with standard scheme of symbol and units and abbreviation was developed and recommended by General Conference on Weight and Measurement in 1971. Okay, and this is the system of unit which is at present acceptable all over the world. And SI system uses decimal system, and therefore conversion within the system are quite simple and convenient. Now the fundamental units in SI system. These are the thing you can see. If you see the quantity, for length it is L, for mass it is M, for time it is T. Okay, for electric current it is ampere. Okay, thermodynamic temperature Kelvin, light intensity candela, amount of substance mole, and these are the symbols that we are having. And here you are seeing that SI units for length meter, mass kilogram, time second, current ampere, Kelvin, candela, mole, and they have their definite symbols also. These are the symbols for those specific units. Okay, and here the supplementary units. Two things are there: plane angle and solid angle. We'll discuss what is plane angle and what is solid angle. For plane angle, it is radian, and for solid angle, it is steradian. So rad, SR. Okay. Now definition of SI units, like how do you define meter? Okay. So the meter is the length of the path traveled by light in vacuum during the time interval of 1 divided by 299,792,458 of a second. So it is 1983 this definition was given. Okay, and kilogram, the kilogram is equal to, so this is a standard thing, like they are comparing with the reference, like uh, suppose they calculated the light travels, how much path the light travels in vacuum in this much of time interval, 1 divided by this much of time interval, and that is equal to 1 meter. Similarly, kilogram. Kilogram is the equal to the mass of the international prototype of the kilogram. So that is a platinum iridium alloy cylinder kept at International Bureau of Weights and Measures at Sevres near Paris, France, 1889. Okay. Second, so here this thing second also changes actually, like this definition 1967 na, the second is the duration of like 9192631 periods of radiation uh, corresponding to the transition between the two hyperfine level of the ground state of cesium 133 atom. So that is actually developed in 1967. Okay, and ampere, it is the constant it is that constant current which if maintained in two straight parallel conductor of infinite length of negligible circular cross section and placed 1 meter apart in vacuum would produced between these two conductors of force 2 into 10 to the minus 7 Newton per meter of length. So these definitions are actually you know basic fundamental information that you should know, but perhaps you will get this type of questions in your examinations. Okay, now here the Kelvin and Candela, they have some definite you know definition for each of them. Now plane angle, you see the plane angle, this is important. Plane angle, so you can see it is d theta is the ratio. So plane angle d theta is the ratio of arc ds to the radius r, and SI unit is radian. You can see the diagram, you can see the diagram. So this ds is arc, this one na, this ds is arc. If I just a second. Hmm. Now you see this ds is arc, okay, and this d theta is actually the plane angle, and this d theta is nothing but ratio of ds to r. R is the radius. Suppose this is the center, okay, so this is the plane angle thing. D theta is equal to ds by r. Solid angle, so solid angle, for solid angle it is uh, denoted by the symbol like this, and it is the ratio of intercepted area dA of a spherical surface, and at the apex O uh, as the center to the square of r. So it actually looks like this. If you take an example of suppose you take example of watermelon, okay, and suppose you have a watermelon, okay, you have a watermelon, you cut a portion over here on the surface of the watermelon and try to get a piece, chunk of piece, which is which has a apex point at the center of that watermelon, okay, then that piece actually looks like this only. Suppose this is the area that is outer side, and this is the conic, you can say uh, this portion is that conic part of it. So it is defined by dA. dA means this surface, and if this is the radius, so dA by r square. dA by r square is for the solid angle. Now the important thing, the following conventions are adopted while writing a unit. First, even if a unit is named after a person, the unit is not written in capital letters. That is, we write joules, not joules means small in lowercase j, okay, not in uppercase. For a unit named after a person, the symbol is a capital letter, that is j, capital, that is uppercase j, and the rest of them is lowercase. Uh, like if you want to write it in this way, only if you want to get uh, only the first letter of it, then you can write like this, or you can write, okay, you check here. For joules you can write either this or lowercase, correct. For other things, like second and all these things, all should be lowercase. The symbol of unit do not have plural form. Like you should not write, if you write 70 meter, it is 70 m only, not 70 ms meters or something newtons. Okay, not like that. Punctuation marks are not written after the unit. Like if 100 cc or 1000 cc, so only like this, not c full stop c full stop like this. Okay, some units are retained for general use, like these things. uh, these things like minute, 60 second conversion, you see 60 minute is equal to 3600 seconds, 24 hours, like this. And degree, it is also important. So actually here it should be written, just a second. Yes, 1 degree is equal to, actually 180 degree is equal to pi radian. So 1 degree is equal to pi by 180 radian. Okay, now if you see this thing, uh, just a second, let me take another highlighter. Yes, now see, this should be 1 degree, not 10. This should be 1 degree. Okay, 1 degree is equal to pi by 180 radian. Okay, so these things are there in your book. I'm not going to explain this thing that much. This is not the basic things, actually conversion of basic things. Okay, and here you have some other points that I'm going to discuss. First thing, hmm, measurement of length. Okay, so measurement of length is very much interesting. We have very small measurement like 10 to the power minus 14 meter, that is radius of a nucleus. 2, so this is the lowermost value we can, basically least value we can measure in distance, in terms of distance. And this is the highest value that we can measure, like radius of universe, 10 to the power 25 meter. Okay, so the distance ranging from 10 to the power minus 5 meter to 10 to the power minus 2, sorry, 10 to the minus 5 to 10 to the power 2, 10 to the minus 5 to 10 to the power 2 meter can be measured by direct method. Direct method means what? Direct method which involve like comparison of the distance of length to be measured with a standard length like meter scale, or maybe some different thing directly you can measure. Okay, see, a meter rod or meter scale can be used to measure distance as small as 10 to the power minus 3 meter. A vernier caliper can be used to measure as small as 10 to the power minus 4 meter. Screw gauge. Screw gauge used to measure as small as 10 to the power minus 5 meter. So for very small distance or very large distance, indirect method are used. So the distance that ranges from 10 to the power minus 5 to 10 to the power 2 can be directly measured, but the distance which are smaller than these 10 to the power minus 5 or larger than 10 to the power 2, that has to measure by indirect method. Okay, now measurement of large distance. The following indirect methods may be used to measure very large distance. What are the things? Parallax method, that is the first thing, parallax method. Actually in class I have discussed parallax method. So in parallax method, basically the distance between one planet to star, like that, bigger distance you can do. Okay, so P is the planet. If you have, okay, this P, so P, suppose a point, it is there, a planet. So let us consider a far away planet P at a distance d or 2 eyes. Like if suppose it is like this, Okay. So suppose this is a planet, P is a planet. Okay, this is a planet. It is at a distance d from these two points L or R. Suppose these 2 points. Suppose we can consider, suppose this is a this is Saturn. Okay, Saturn, and this is Earth. So we are on Earth, so that is why we can see it is little bit bigger. So from these 2 points, if we measure, if you imagine a triangular shape, okay, then suppose the lines joining the planets to the left eye L and right eye R subtended an angle theta. So theta is means this is the angle theta. Okay, therefore you will get this triangle. Now the angle theta is called parallax angle. This theta is called parallax angle or parallactic angle, and the distance LR. LR means distance from this point to this point. This is LR. See, or LR is actually given here B. The distance is given B. B is known as basis. Okay, as the planet is far away means how can you conclude the planet is far away? If you get a ratio B by D, and if that is very less than 1, if you get a ratio B by D in that is very less than 1, that means B by D means a ratio where you have numerator to of this length and denominator of this thing, correct? If this ratio is very less than 1, and therefore your theta will be very small. Okay, very less than 1 means what? With compared to this B, this D is very large, very large. So if this B is not that much large but D is very much large, so that means the angle between these two, things like this angle should not be that much, large. It should be small, very small. Okay, and then taking the distance LR as B, and as the circular arc radius D, that is this is the circular arc radius D. What we can do, we can do theta is equal to LR by D. Theta is equal to LR by D, or LR is equal to B, so theta is equal to B by D. Now theta is equal to B by D means D is equal to D means the distance. You need the distance now. Your aim is to take the distance from L to P or R to P, because you need to measure the distance, no, the distance between the planet and to these points. Okay, so therefore this D is the final answer. Capital D is the B by theta. Theta is the parallactic angle or parallax angle, and B is the basis of it. Okay, now measurement of size or angular diameter of a astronomical object. See, D here you can see of an astronomical object, and it is E is denoted by Earth. It is Earth. Now from Earth, if you basically create an apex point on Earth, and if you consider whatever the astronomical object was there, uh, from that, along the diameter of them, if you consider two different points, you can consider A and B here, and the distance between A and B is nothing but the diameter of that astronomical object. So again you will be getting this angle, and what we can consider here, you can consider angle theta. Okay, so angle theta, same concept. So we know earlier, we know, what do you know, like uh, this small d by capital D. Okay, the small d by capital D. So here they have considered it alpha instead of theta. So that is up to you. You can consider anything. Okay, so then what you can consider, theta is equal to small d by capital D, or alpha is equal to small d by capital D. See, here I have considered theta and they have considered alpha, but both of them are similar thing. Okay, this is up to you. Now the angle alpha can be measured from the same location on the earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through the telescope. Whenever you are viewing through the telescope, you can use this method. Since capital D is known, the diameter of the planet can be determined. See, this type of thing, when we use this method, earlier I have showed you to determine capital D. Capital D means when you don't know about the distance between one planet to that Earth or something, then you can use that thing. Here we know the distance from Earth to that specific planet or astronomical object, and at that time, if you know the value of the capital D, then you can get the value of small d as well. Okay, so small d is equal to alpha into capital D. Now, echo method or reflection method. This is also indirect method to measure the distance. This method is used to measure the distance of hills. Suppose this is a hill. If we fire gun and then it reflect back, so it approaches to the hill. This is the surface of the hill. On the surface, it get reflect back, and it is received by the echo receiver. So gun is fired towards the hill, and the time travel between the instant of firing the gun and the instant of hearing this echo of a gunshot is noted. Okay, and this is the time taken by the sound to travel from the observer to the hill and then again hill to the observer. So twice the distance. So if v is the velocity of the sound, s is the distance of the distance of hill from the observer, what you can say, we know it. If t is the total time, so t is nothing but to, time is what? If you know velocity is equal to displacement by time, distance by time, so time is equal to displacement by velocity is equal to displacement by time. So time is equal to displacement by velocity. So displacement was for going it is s, coming also s, so 2s. So 2s by v, that is the time. Time is equal to 2s by v. Okay. So if it is so, then what you can say, s is equal to v into t by 2. So distance, if you want to measure, that is v into t divided by 2. Okay. Now, in a place of sound wave, in place of sound wave, laser also can be used. But laser measure the distance of moon from Earth. Laser is monochromatic, intense, and unidirectional. That is why the laser beam are used. If t, small t, is the time taken for a laser beam is going to and returning from the moon, then the distance can be calculated by using the formula s is equal to small c into t by 2, where c is equal to speed of light in vacuum. So 3 into 10 to the power 8 meter per second. Now estimate very small distance. While estimation of very large distance, uh, uh, estimation of very large distance, we can measure by the parallax method. The estimation of very uh, uh, very small distance also can be measured. Okay, using electron microscope, we know can do. Electron beam can be focused by properly designed electric and magnetic field. Okay, then we can do. And the resolution of such an electron microscope is limited finally by the fact that electron can also behave as wave. Okay, so these things are not that much important. Now Avogadro method also there. So a simple method for estimation of molecular size of oleic acid that I have done in class also. Oleic acid is a soapy liquid which is having large molecular size of in the order of 10 to the power minus 9 meter. So the idea is to first from monomolecular layer of oleic acid on the to form monomolecular layer of oleic acid on the water surface. Monomolecular layer means layer should contain one molecule. Like suppose you have water here. Just a second. You have water over here. Suppose this is water. Monomolecular label means single molecules in this layer of oleic acid, like this. On the surface of water, you have single molecular layer. Okay, this is monomolecular layer. Okay, so now coming to that. Okay, so you need to form a monomolecular layer of oleic acid on water surface. Then we dissolve 1 centimeter cube of oleic acid in alcohol to make a solution of 20 centimeter cube. Okay, then we take 1 centimeter cube of this solution and dilute it to 20 centimeter cube using alcohol. Okay, so the concentration of the solution is 1 divided by 20 into 20 centimeter cube of oleic acid per centimeter cube of the solution. Therefore, what we can do, we need to first sprinkle some amount of lycopodium powder on the surface of the water in a large. So that means that lycopodium basically, why we sprinkle that thing, because this oleic acid thing is there now, because the oleic acid you have basically diluted with the help of alcohol, so you need to separate it from that. Oleic acid should be separated from that alcohol, so that is why you have given the lycopodium powder. So oleic acid drops spread into thin, large and roughly circular film of the molecule thickness on the water surface. Now then we quickly measure the diameter of the thin film to get the area. Suppose we have dropped n drop of water. Initially we determine the approximate volume of each drop. Let's suppose V. Then volume of n drop is n into V. Okay. Each drop is V centimeter cube. N drop is n into V centimeter cube. And now we know the thing, like amount of oleic acid in this solution, because previously what we know, here we know the concentration of the solution. It is given the concentration of the solution is 1 by 20 into 20 centimeter cube of oleic acid per centimeter cube of the solution. Now that we should use over here in this case, the volume of n drop of solution is nv centimeter cube. Amount of oleic acid in this solution is nv into 1 divided by 20 into 20, that is 400 centimeter cube. This solution of oleic acid spread very fast on the surface of water and forms very thin layer of thickness small d. Now this thickness is very important. If this spread to form a film of area A centimeter square, then the thickness of the film T is equal to volume of the film divided by area. Because volume having 3 dimensions, so if you getting the thickness means it should be volume by area. 3 by 2 dimension, then you will get 1 dimension. Okay. So T is equal to NV divided by 20 into 20 into A. So if we assume that the film has monomolecular thickness, monomolecular I said you, one molecules side by side. So the thickness of the layer is nothing but basically size of the or diameter of the molecule. Okay. So in that way you can basically find it out. Now range of lengths, the size of the object we come across in the universe varies over a very wide range. This may vary from the size of 10 to the power minus 14, a tiny molecule, to 10 to the power 26, 10 to the power 26 extent of the observable universe. So we also use certain special length unit of length for short and large lengths which are given below. Like Fermi, 1f, 10 to the minus 15 meter, 1 angstrom, 10 to the minus 10 meter, 1 astronomical unit AU, 1.496 into 10 to the power 11 meter, 1 light year, 9.46 into 10 to the power 15 meter. and 1 parsec 3.08 into 10 to the power 16 meter. So we do have the definition for astronomical unit, average distance of sun from the earth, and we do have 1 light year definition for 1 light year, the distance that light travels with a speed of 3 into 10 to the power 8 meter per second in 1 year. Then 1 parsec, the distance at which the average radius of the earth's orbit subtend at an angle 1 arc second. Now range and order of length. So this is the longest to the shortest, like this. So these are the ranges, like size of proton 10 to the minus 15 from Fermi to how it is basically going to that 10 to the power 26. Now measurement of mass. So measurement of mass, we know SI unit is kilogram, and prototype that I have described. So this is not that much important. And here we should know, like dealing with the atom and molecule, the kilogram is an inconvenient unit, correct? Because in that case there is an important standard unit of mass called unified atomic mass unit, U, which has been established for expressing the mass of an atom. So that is 1 unified atom mass unit is equal to 1 U, and 1 unified mass unit is equal to 1 by 12 of the mass of an atom of carbon 12 isotope. Okay, so 1 U is equal to 1.66 into 10 to the power minus 27 kg. Now method of measuring mass by common balance, that is the basic thing. Large masses in the universe like planets, stars, etc., based on the Newton's law of gravitation can be measured using gravitational method. For measurement of small masses of atomic and subatomic particle, we make use of mass spectrograph, in which radius of the trajectory is proportional to the mass of a charged particle moving uniform electric and magnetic field. Then range of masses, the masses of the objects we came across in the universe vary over very wide range. Like in length also we see from very least value to the very big value, we can see large value. Now here also, like from ranges of masses also in the order of 10 to the power minus 30 kg to, that is 10 to the minus 30 is actually of electron, to a huge mass about 10 to the power 55 that is known for the universe. So range is 10 to the march, that's mass largest to the mass smallest 10 to the power 85 is to 1. So this is the range. So see the electrons 10 to the minus 30 from the observable mass of universe 10 to the minus 10 to the 55. So this is the range. Okay, so these are actually the concept you should know about it. There is no hard and fast rule to mug up all these things. Okay, now we'll see something not in this way. We'll see time also. This cesium clock is there. Now this accuracy precision of the instrument and errors in measurement is something that we should discuss in class only, but now we'll do, because we know the basic things of it. Errors, like if we know little bit of it, not go deeper to it, like because I like to discuss this thing more frequently in offline classes, because this thing, if I use some practical example, then you can understand this concept. Okay, now error, the result of every measurement by any measuring instrument contains some uncertainty, and that is called error. What do you mean by accuracy? In my class I have given some example, like the accuracy of the measurement is measure how close the measured value with the true value. And precision, this is what resolution or what limit the quantity is measured. Okay. Now example. Suppose the true value of a certain length is near to 2.874 centimeter. You just see the example, then you will understand. In one experiment using measuring instrument resolution of 0.1 centimeter, the measured value is found to be 2.7 centimeter. So true value is what? You see the true value. True value is 2.874 centimeter. Now you are using an instrument which is having 0.1 centimeter of resolution, and you are getting the value to be 2.7 centimeter. While in another experiment using the measuring device greater resolution, not this much resolution, say 0.01 centimeter resolution, you get 2.69 centimeter. Then the first measurement has more accuracy because it is close to the true value. 2.7 is close to 2.874. 2.874 is the true value, but it is less precise because the precision, the resolution is 0.1 centimeter. While the second one, measure less accurate but more precise, because you see 2.69 is more precise value because you are having resolution of two decimal place. After decimal you have two places, correct? So having more resolution, but still it is less accurate because it is not very close to the true value. Okay. Now errors are also there, like in general errors can be like systematic error and random error. Systematic error, the systematic error, that error caused due to the you know it can be positive or negative. Suppose you want to measure some value, you are getting, instead you want to measure 5.5, you are getting 5.6, so plus 1, plus 0.1, or you are getting 5.4, so minus 0.1. So this type of thing, either in positive or negative direction you are having. Some of the source of the systematic error, instrument error. Okay, like due to the instruments and calibration, instrument, you do have some calibration error. So we know na, before going for measurement you should calibrate your instrument. Calibration means, let's suppose take an example of weighing machine. First you should step on to the weighing machine, and before stepping onto the weighing machine you must confirm the weighing machine's reading should read 0, and that is what it is calibrated or not, you can understand. Okay. The temperature graduations of a thermometer may be inadequately calibrated. It may read 104 degrees centigrade at boiling point of water at STP, whereas it should read 100 degree. Okay. In vernier caliper, the zero mark of vernier scale may not coincide with the zero mark of the main scale. Okay. So these are the instrumentation error. It is there. An ordinary meter scale may be worn off in one end. Meter scale, if it is made of wood or something, or maybe metal, it have wear and tear. So due to the wearing of the metal or wood or something, it might not having the original length of 1 meter. So due to that also error can occur. Now imperfection in experiment technique or procedure, that also can occur. Personal error also, they are taking the individual reading, carelessness, all these things. Okay, that is there. And systematic error can be minimized, improving the experimental technique, selecting the better instrumentation, removing the personal bias as far as possible. And then random error I actually discuss in class, that is if certain conditions are there. Suppose it is not supposed to like in regular pattern something occur. If you are doing an experiment of pendulum, time period of pendulum, certain gust of wind creates problem in your experimental room, in you are getting errors. Okay, due to some personal error also, observer not taking the correct reading, fluctuation of reading can occur. Okay, when the same person repeated the same observation, it very likely that he may get different reading every time. Okay. And least count error. So the smallest value that can be measured by the measuring instrument is known as least count. Least count error is the error associated with the resolution of the instrument. Suppose if you consider your meter scale, the least value you can measure 1 millimeter. Okay. So in that case, what you can consider, the smallest value is millimeter. Now if you are using a vernier caliper, you can get other, smallest division within that millimeter also. So the resolution of the instrument get increased. If the resolution of the instrument get increased, that means less chance of getting least count error. Okay, vernier caliper has least count of 0.01 centimeter, whereas spherometer having a least count of 0.001 centimeter, so having more resolution. So using instrument of higher precision, improving experimental technique, you can reduce least count. See, more decimal places after this, you know this 0.001, so you have three places, and 0.01 two places. So this spherometer having, much more accuracy. Okay, even if you repeat the experiment, then also you can basically uh, avoid the error. Okay, now absolute error, the magnitude of the difference between the individual measurement value to the true value, is known as absolute error. It is denoted by delta A. Okay, so this thing I might discuss in, class. Now I am avoiding this part, and I'm going to the main, like the dimension part. Okay, dimensional part I will discuss this thing better. I will discuss one problem in class, then you can understand this part. And more CBSC, I think they have basically, many schools have omitted this part. Okay, now the significant figure. The reported result of measurement is a number that include all digits, the number in the number that are known reliably plus the first digit that is uncertain. So the reliable digit plus the first uncertain digit are known as significant digits or significant figures. Example, let's take an example. The period of oscillation of a simple pendulum is 2.36 second. The digit 2 and 3 are reliable and certain, while digit 6 is uncertain. Thus, the measured value has three significant figure. Okay, so combination of the certain and uncertain thing should be there. Now, the length of an object reported after measurement, suppose 287.5 centimeter. So it has four significant figure. So the digits 287 are certain value, and 5 is uncertain value after the decimal. Note, a choice of change of different units does not change the number of significant digit or figure in the measurement. The length 1.205 centimeter or 0.01205 or 12.05 mm, or suppose 12050 micrometer, all have four significant figure. How? Because you see the first case, if you consider the first case 1.0205, here you have, this is certain and these are all uncertain, still all of them are significant. See, zeros between 2 and 5, because this 2 is significant, 5 is significant, so that is why 0 is also significant. Now if you have this next one 0.012, here what you have after the decimal, you have this 0, this is not significant. 1 is significant, 2 is significant, 0 is significant, 5 is, so 4, again 4 significant. 12.05, here also you have 1 2, these two are certain and significant, whereas after the decimal you have 0, but after that also you have some value, so it is having significant four significant, figure. But why in this case you don't have this, you don't consider this 0 to be significant? Suppose 0.0125, after 0 you have 1 significant, but before 0 you have decimal and then again 0. So that is why these two zeros are not considered. Then 12050. Here also you have four significant. How? This is one significant, this is one significant, this is one significant, this is one also significant, but this last zero is not significant. So you have four significant in each of these cases. So rules for determining the number of significant figures. All the non-zero digits are significant. All the non-zero digits are significant. All the zeros between two non-zero digits are significant, no matter whether the decimal point is. Okay. 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 So all non-zero digits are significant. All zeros between two non-zeros. You have 102. So you have 102. So 1 is significant, 2 is significant because both of them non-zero. So 0 is also significant because it is in between two non-zeros. Okay. Acha. Next, if the number is less than 1, less than 1 means 0 point something like that. The zeros on the right of the decimal place, the zeros on the right of the decimal point, but to the left of the first non-zero digit are not significant. That is what I am saying earlier. 0.01205 like that you have. So what they said, if the number is less than 1, this is less than 1, the zeros on the right of the decimal. So this is the decimal. Zeros on the right of the decimal is this one, but to the left of the first non-zero. So this is the first non-zero 1. So this 0 is left of that first non-zero. So that is not significant. Okay. Next, this one. The terminal or trailing 0 in a number without a decimal point are not significant. You don't have a decimal point. Suppose you have 1250. So the trailing or terminal 0 in a number without a decimal point. If you don't have a decimal point here, so this doesn't have any meaning, not significant. Okay, but here we do have a very important point. Suppose you have suppose you have 1250, 1250, same thing, but I have written here meter. I have given on unit. Then this 1250, these four digits are actually significant. That time 0 is also considered because you have given a unit. So two conditions, terminal zeros, if there is no unit, that doesn't have any significance. But the terminal 0 is there, but you have unit, then terminal 0 is also considered to be significant. Correct? The trailing 0 in a number with a decimal point are significant. Yes. Suppose you have 12.0, then 123. You can consider. Now scientific notation. Any given number can be written in the form of this: a into 10 to the power b, like that. Anything. So suppose 350 is there. So it can be written 3.5 into 10 to the power 2, or 35 into 10 to the power 1, or 350 into 10 to the power 0. 10 to the power 0 means 1 only, na? Okay. So a into 10 to the power b means a times 10 raised to the power b, where the exponent b is the integer, is an integer, and the coefficient a is a real number called significant in that case. Okay, but suppose you have this type of thing, let's say 3.5 into 10 to the power 2, then what will happen? This 3.5 into 10 to the power 2, so this 10 to the power 2 should not have any significance, only 3.5 having significance, and obviously there is two significant figure. Correct? Suppose you have 10 to the power something that doesn't have any significance. If the number is negative, then the minus sign uh, precede a as a ordinary decimal notation. Okay. In normalized scientific notation, the exponent b is chosen such that the absolute value means uh, mod means what, positive thing only, huh? It should not take any negative, of a remains at least 1 but less than 10, the absolute value of it. Okay. For example, 350 can be written 3.5 into 10 to the power 2. Okay, but it should at least 1, it should be at least 1. Like writing 350 into 10 to the power 0 is actually foolishness, and that is not way to represent it. You can write, so it's the 35 into 10 to the power 1, or 3.5 into 10 to the power 2. Okay, or 0.35 into 10 to the power 3, that is also okay. These forms allows easy comparison of two numbers of the same sign in a, as the exponent b gives the number order of the magnitude. If so, this condition is when this a term means this term is negative in nature. Rules of for arithmetic operation with significant figures is very important. We must know this thing because many questions, so let's suppose in school or in JEE special, this type of question in JEE means need this type of question asked again and again. In arithmetic operation, the final results should not have more significant figure than the original data from which it is obtained. What type of thing? Multiplication or division, the final result. So when you do the multiplication or division, either multiplication or division, the final result should retain as many significant figure as are there in the original number with the least significant figure. Example, so and for addition also, like the addition or subtraction, the final result should retain as many decimal places as there in the number with the least decimal places. Suppose if I am considering that thing for multiplication or division, this thing I'm saying, suppose you have 2.1 into 12.2. So in 2.1, how many significant? 2, 2 and 1, and here it is 1, 2, 2, so 3. So the result, whenever you're doing the multiplication, I do the multiplication and the result should be with two significant figures, because the least significant figure should be there. That means when you multiply 2.1 into 12.2, the result should have least significant figure with the, with the original value with whom you are multiplying. For division also the same thing. Suppose you are dividing 12.4 by 2.1, so the division value should be have two significant figure. Okay. For addition and subtraction, here the decimal places is having importance. Like the final result should retain as many decimal places as there in the number with the least decimal places. Suppose 12 to 1 to 3.6 with you are adding with 2.1, or 1 to 3.66 with 2.1. So here you have least decimal places to is 2.1, and here it is 2 1 to 3.66, so two decimal places. So what you should do, you should add it and you should get the minimum decimal places. The minimum decimal places, you see, this is the minimum decimal place. So answer should have minimum decimal place, so it should be compared with the minimum decimal place. Suppose this 2.1 is here na, so least decimal place, the answer should be with that thing. Now rounding of the uncertain digits. Rounding of a number means dropping of digit which are not significant. The following rules are followed for rounding of the number. If the digits to be dropped are greater than 5, then add 1 to the preceding significant figure. If the digit to be dropped is less than 5, then it is dropped without bringing any change to the preceding number. If the digit to be dropped is 5, not less than, not more than, only 5, then the preceding digit will be left unchanged if the preceding digit is even, and it will be increased by 1 if it is odd. What? Acha, let's see an example. Suppose you have 2 point you have 2.65. I ask you to get one decimal place, so it should be, so the one decimal place means after decimal one place, so this 5 has to be dropped, it 5 has to be dropped. But you see, the 5, before 5, what is the preceding number? Preceding number is 6. So 6 is actually even, so there should be no change, it should be 2.6. Okay, now uh, if you have 2.76, one decimal place you need to show, you need to round up one decimal place, so after decimal one place there, so 6 is 5, 6 is greater than 5. So if it has to be dropped, if it has to be dropped, then what you should do? If it has to be dropped, then what you should do? You should add 1 to the preceding. Okay, you should add 1 to the preceding, so it should be 2.8, it should be 2.8. Okay, then you see, if you have a digit, see this thing, if you have a digit 2.44, if you want to have one decimal place, after decimal you need one place, you need to go one place, but you need to go one place na, so you need to go one place means this 4 has to be dropped, but 4 is less than 5, so it should be unchanged, 2.4. Okay, this is how you should do. Now dimension of the physical quantities, this is much more important thing, you should listen it very carefully. The nature of physical quantities is described by its dimension. The nature of the physical quantities, all the physical quantities can be expressed in terms of 7 base or fundamental quantities. 7 base or fundamental, what are those? What are those 7 base or fundamental quantities? Mass, length, time, electric current, thermodynamic temperature, intensity of light, amount of substance. Okay, all these things. So mass means in dimension, what we should write for mass? M, capital M. For length it should be written capital L. For time it should be capital T. Electric current ampere, and thermodynamic temperature Kelvin. Okay, intensity of light CD, amount of substance mole. Okay, okay, now you see, the dimensions of physical quantity are the powers or exponents to which the fundamental or base quantities are raised to represent the quantity. Okay, what is that thing? Acha. Now another thing you should remember, if you represent a dimension, you should use a square bracket. This is the square bracket, you know. This you should represent, if it is mass, it should be like this. Okay, suppose for force, you see, for force is what? Mass into acceleration. Mass is m, acceleration is meter per second square, so length t to the power minus 2, so m l t to the power minus 2, this is the fundamental dimension for force, m l t to the power minus 2. Okay, Okay, now uh, we should check. Okay, now we should check the next thing, that is uh yes, this one actually I was describing. Okay, now uh, hmm, before that, okay, the dimension of the volume is what? L cube, meter cube na, L cube. Force, I actually wrote it. Energy means it is near to the work done, and work done is what? Force into displacement. So force is actually having ml t to the power minus, sorry, force is actually having ml t to the power minus 2, and you are having the distance is l. F is f into s na, so distance is l. So you will be having ml square t to the, sorry, m l square t to the power minus 2, ml square t to the power minus 2, that has to be there. Just a second. Now if you want, if I say you, what will be for power, what will be for power, what will be the the dimension for power? Power is what, you know, work done by time or energy by time, you can do anything. So you already get ml square t to the power minus 2 divided by time. Okay, so it should be ml square t to the power minus 2 by t, that means t to the power minus 3 for power, you will get like this. Okay, okay. Now the dimensional quantity. Dimensional quantity is a physical quantity which has basically dimensions. Speed, acceleration, momentum, torque, all these dimensional quantity. What do you mean by dimensionless quantity? Dimensionless quantity is a physical quantity which has no dimension, like relative density, refractive index, strain. That is ratio of the same physical quantity is actually dimensionless. Suppose you are considering strain. Strain is change in length by original length. So it is dimensionless quantity. What do you mean by dimensional constant? Dimensional constant is a constant which has, that is also having dimension, like G, capital G, capital G. That is having its own dimension. Okay. Even we can consider other things like for Coulomb's law or electrostatic, you have a value of k, that is also having dimension. So that constant is also having dimension. So all constant, it is not like that all constants not having dimensions, but certain constants having dimensions also. Those are known as dimensional constant, like universal gravitational constant, Planck constant, Hubble constant, Stefan constant, Wien constant, Boltzmann constant, gas constant, universal gas constant. In chemistry, you might have know R, capital R. Faraday's constant, all are actually dimensional constant, and from this actually question may asked from these constants. Okay, and dimensionless constant, that basically having no dimension, like any numbers, any integers, any pi or that type of thing, e, all these things. Now the dimensional formula and dimensional equations, it is very important, huh? The expression which show how and which of the base quantities represent the dimensions of a physical quantity is known as dimensional formula. Let's suppose take example of basic thing like dimensional formula of volume. See, volume only L cube but you should give other fundamental dimensions like M and T also should be there. But M doesn't have any power to it. So M raised to the power 0 over here. And T also raised to the power 0. And their order should be M, L, T in that order, in that specific order. It should be in that specific order. You should not write, first L, then M, then T, or first T, then L, and then M. It should be MLT. If your physical quantity doesn't have that significance in this mass, then it has to be m raised to the power 0, like the volume and this time also. Okay, formula for speed, again m is 0, m raised to the power 0, but length is there, length per time, so l t to the power minus 1. Dimensional formula for acceleration, m raised to the power 0, l t to the power minus 2. Acceleration l t to the power minus 2. An equation obtained by equating a physical quantity with its dimensional formula is known as dimensional equation of the physical quantity. Okay. Example. Suppose you have volume that we have written like this. Okay. But you see V. See, both of them are different. This is volume, this is speed. Okay. So that means whenever you note with the perfect notation, you should give, like for volume it should be capital V, for velocity it should be small v. In that case, acceleration it is like that. Okay, now quantities having the same dimensional formula, like impulse and momentum. Impulse and momentum. Momentum m into v. Impulse also having the same dimension. Work, energy, torque, and moment of force, all are actually having same dimension. Angular momentum, Planck constant, rational rotational impulse. Why it is so important? If you remember some of them, na, they have saving the same dimension. If you remember dimension of any one of this physical quantity, then you can, if you know the dimension of work, you know the dimension of energy, torque, moment of force, all of them. If you know dimension of angular momentum, then you can basically write this is the same for the Planck constant. So this is a hack in examination. No need to remember all these things. If you remember, if you remember which are actually having that same dimensional formula, then you can apply for that. Stress, pressure, modulus of elasticity, even the energy density, all are actually having same dimensional formula. Four constant, surface tension, surface energy. Surface tension, surface, because see, most of the time they can ask you Planck constant, modulus of elasticity, surface tension. They can ask you the dimensions for them. Frequency. Okay, gravitational potential and latent heat, both are actually having same dimensional formula. Thermal capacity, entropy, and capital R, universal gas constant, and Boltzmann constant. Force and thrust having same dimensional formula. Power and luminous flux. Power already we have derived, ml square t to the minus 3. That should be for luminous flux also. Okay. Now, some dimensional formula that are used in physical quantities, often used in physics, are given at the end slides. Okay. Now we'll see dimensional analysis and its application. Very much important. This part is very much important. Okay. Dimensional analysis is a tool to find or check the relations among the physical quantities by using their dimensions. Okay. When magnitudes of two or more physical quantities are multiplied, their unit should be treated in the same manner as the ordinary algebraic symbol. We can cancel identical units in the numerator and denominator. Similarly, physical quantities represented by the symbol on both sides of a mathematical equation must have same dimension. That means what? Let us see one thing. Acha. Before that, we should see all the things. Like dimensional analysis can be used to check the dimensional consistency of an equation. That means dimensional homogeneity also. It is said that principle of homogeneity of the dimension. Then to convert units in one system to another system, we can use, and to derive a relationship between physical quantities based on certain reasonable assumptions. Okay. Now, what we should do checking the dimensional consistency of an equation? First, principle of homogeneity. The magnitude of physical quantities may be added together or subtracted from one another if they have same dimension. Otherwise, it should not be having, you should not do that operations. Acha, let us check who are there. Just a second. Oishi, Nibo Lodika is there. Okay, 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 okay. So, okay, what I was talking that according to the principle of homogeneity, the first concept, the physical quantities must be added together or subtracted from one another if their dimensions are same. That is the first thing. Initial velocity can be added or subtracted from the final velocity. Why? Both of them having same dimensional formula. What is the dimensional formula for them? M raised to the power 0 L T raised to the power minus 1. Correct? But force and momentum cannot be added because their dimensions are different. For force, it is mlt to the power minus 2, and for momentum, it is mlt to the power minus 1. To check the dimensional consistency for v square is equal to u square plus 2as, I'll be doing it in separate board. Okay, in blackboard, I'll be doing it. So what I have to check? I have to check v square is equal to u square plus 2as. For left hand side, v square. V is what? Dimensionally. You can write m0 L t to the power minus 1, but it is square. Okay. So you can write it. It could be written this thing L. Sorry. Just a second. Yes. Then L square t to the power minus 2. Okay. But for RHS, see u square, the same thing, m0 L t to the power minus 1 square and 2as plus 2a m0 L t to the power minus 2. And then we do have s also. Else means m0 L t to the power 0. Only the distance, correct? So you may ask me why you should write all time m0, but it is not there. This is up to you because they will not, they basically deduct the marks if you are not omitting this m because it doesn't have any value. Okay, in that case. Okay, no problem. See this thing, m L squared t to the power minus 2 plus this 2 is insignificant in this case because doesn't have any dimension. Okay, so you can basically omit it. Here the dimension you check, m m0 L square t to the power minus 2. So RHS, so this RHS is again same with the LHS. Whatever LHS, there individually RHSs are the same thing. So the first concept, if it is not dimensionally equal, then you cannot add them. That is why you can add u square with 2s, and whatever the value you are getting individually, that has to be equal with this LHS also. So you can say this formula is dimensionally true. Let's take example of other thing, other concept. Suppose you have v is equal to u plus at. Then you know this thing L t to the power minus 1 over here, and here it is L t to the power minus 1. Acceleration is L t to the power L t to the power minus 2. Okay, acceleration is L to the power minus 2. Just a second. Acceleration is L t to the power minus 2. L t to the power minus t to the power, yes, minus 2, and then t is only t. So if you consider both of them, then it should be again here lt to the power minus 1, and here also lt to the power minus 1, and it is also plus lt to the power minus 1. Correct? All are same. So this is how you can justify, or you can compare, or you can analyze, or you can basically prove this formula is correct, because you cannot add any physical quantity if they are dimensionally not equal. So you can add u square with 2s because they are dimensionally equal. And if equation is not correct if the right hand side dimension is not equal to the left hand side dimension, here also the same. You don't have any confusion na. See, this thing cannot be added. You, if you see the add also, it should not be added. Like this means they both are having the same dimension. That means they can, this plus sign is there na. But you should not confuse with we have to add again. No, not like that. Okay. Now again we'll check the next thing that was there. Yes. So to check the dimensional consistency, I actually show you how to check it. That's what they have given in here. Okay. See, note 2 is constant in terms of 2s. So 2 doesn't have any dimension. Okay. Okay. So each term of the above equation is having same dimension. Therefore, the given equation is dimensionally correct or dimensionally consistent. Note. If an equation fails to consistency test, it is proved wrong. That means the equation is wrong. But if passes, that means it is right. So it is not like that whatever equation you will be having as a student of science, you will blindly believe on it. You have to check with the dimensional analysis, then only you can basically agree with the equation. Okay. Thus a dimensionally correct equation need not to be actually an exact or correct equation, but dimensionally wrong or incorrect or inconsistent equation must be wrong. That means what? Suppose dimensionally you prove a equation is dimensionally correct, but it is not exactly a correct equation. It must be, it can be, because you can equate simply, suppose you have two physical quantities different thing, you are equating with the dimension, because they have same dimension, but the equation is not correct practically in terms of physics. But that thing is there. That means if it is dimensionally correct, that doesn't means you have the exact equation. But if somebody says you have a equation, then you need to justify it, it must be dimensionally correct, because if it is dimensionally wrong, incorrect, then the equation must be wrong. Suppose equation v square is equal to u square minus 2as, or v square is equal to u square plus half as, all are dimensionally consistent in terms of mechanics. But see, though this minus 2as is somewhat correct, somewhere it is correct, somewhere, because you know, if we consider retardation, it is somewhere correct. But plus half of as is not at all correct. Or if I write v square is equal to u square plus as, this is also dimensionally correct. Yes or no? But see, without this 2, it is not correct. Okay. So Albert Einstein tried his famous mass energy equation as E is equal to m by c square, E is equal to m square by c, E is equal to m square c. So he has tried. So this is a real case, you see. Okay. So he tried with, first he tried with m by c square, then m square by c, then m square c. Finally he settled with E is equal to mc square. Why? Using the dimensions. Then it proved it with the help of calculus. That means when a scientist or a student of science thought of some equation, first he has to have some hypothesis on it. Then he has to develop a theory. Then go for the equation and then check dimensionally whether it is correct or not. Then you can prove with the help of a good scientific tool, that is calculus. Okay, to check the dimensional consistency of half mv square is equal to mgh. Half mv square kinetic energy, mg is potential energy, both of them are energy. So first what we do, m is this, we know m is capital M to the power 1. 1 you cannot write it, you can write it, or also you can omit it also. You can write 1 over here, also you can omit it. And there is no provision of L, so L power 0, T power 0, no provision of time also. V m raised to the power 0, L T to the power minus 1, and G m raised to the power 0, L T to the power minus 2, because it is an acceleration. Okay, then H is equal to m raised to the power 0, L T raised to the power 0. Now substituting these dimensions in the given equations, what you will get, both the cases, half doesn't have any dimension, being a constant, but it is dimension less constant. Okay, now for m it is m L raised to the power 0, T raised to the power 0, and V it is m raised to the power 0, L T raised to the power minus 1 square. So it should be m L raised to the power 0, T raised to the power 0, that is m, G m raised to the power 0, L T raised to the power minus 2, and H m raised to the power 0, L T raised to the power 0. Correct? So if you check it, you can understand that if you check this thing, see, yes, definitely half doesn't have any dimension. So both the side LHS RHS both having m L squared T to the minus 2. So it is dimensionally consistent. Again, another concept is there. In place of half mv square is equal to mgh, if I write mv square is equal to mgh, see, though these two sides are dimensionally consistent, but the equation is not correct, because mv square doesn't have any meaning. It should be half mv square, because you know the formula na, kinetic energy, how it is half mv square, because an object is coming with v square is equal to u square plus 2gh, and v square minus u square is equal to 2gh. Okay, so therefore what you can say, h is equal to v square minus u square divided by 2g. Correct? Just a second, check. Okay, so what I am saying, v square is equal to u square plus 2gh, or 2gs, you can say 2gs. So v square minus u square is equal to 2gs or 2as. You can consider, because whenever you are considering kinetic energy na, normally you can consider particle in the motion, so 2as. So s is equal to v square minus u square by 2a. Now what you can do, you can consider, okay, work done is equal to F into S, and work done is nothing but energy. So kinetic energy is equal to work done. So F is what? Ma, Newton second law, Ma, into S. S means V square minus U square by 2A. Now if you cancel out A, it will be mv square minus mu square by 2. So simply you can write half m v square minus u square. Now if you consider, okay, initial velocity to be 0, then it should be half mv square. So half you cannot eliminate na. So that means mv square is equal to mgh is also dimensionally consistent. But if you are not giving half mv square, it is incorrect in practical cases. Correct? Okay. Now conversion of units in one system to another system with the help of dimension. Units are derived from dimensions, and the dimensions are derived from the actual formula of the physical quantity. Okay, if the dimensions are known for physical quantity, then it is easy to express in FPS, CGS, MKS, all this SI, all this fusion system. What we should do? See the formula. N1 in square bracket, M1 raised to the power A, L1 raised to the power B, T1 raised to the power C. This is for one unit system, one system of unit. And next, if you want to convert into another, then has to be N2, M2 raised to the power A, L2 raised to the power B, T2 raised to the power C. Then what you'll be getting? You'll be getting N2 by N1, N2 by N1 as simple thing, na? If you do N2 by N1, this N1, if you just do N2 by N1, then what you should do, or you can do one thing, you just make N2 as subject, N2 as subject. So what you'll do, N1 with the N1, what are the things are there? M1 raised to the power A, L1 raised to the power B, T1 raised to the power C. So you divide with this thing. So M1 by M2 raised to the power whole raised to the power A, L1 by L2 whole raised to the power B, T1 by T2 whole raised to the power C. That is equal to your N2. Now N1, N2 are the magnitudes in the respective system of units. Smaller the unit, bigger the magnitude of the physical quantity, and vice versa. For example, 1 meter to 100 centimeter. M is the bigger unit, centimeter is the smaller unit. So here, what you can say, this is your one thing, and this is your one thing. Like this is, these are the n values. Suppose this is your n2 and this is your n1. 1 Newton is equal to 10 to the power 5 dyne. Okay, so Newton is bigger unit, so having small magnitude, and dyne is smaller unit, must have equal matlab, greater magnitude, so that it can be equated. When you compare with one bigger system of unit with a smaller system of unit, the magnitude for the bigger system of unit should be small, and magnitude for the smaller system of unit should be big. Example, to convert 1 joule in joule to arg. So ERG, okay, so joule is the unit of energy or work in SI system, arg where it is the unit in CGS system. So dimensional formula for energy or work is m L square T to the power minus 2. The units from dimension in SI and CGS systems are kg meter square, centimeter seconds minus 2, and gram centimeter square second to the power minus 2. Okay. Now let N1, this is the thing, na? N1 is the magnitude. N1 joule is equal to N2 arg. So you need to convert it, na? So normally what will happen if joule is actually the bigger unit and arg is the CGS. Actually here it is actually joule is SI system, arg is CGS system. Okay. So what we should consider here, you must make a table. It is a SI system, it is a CGS system. N1 we know it is 1 joule because they ask you 1 joule, but we don't know how much arg. So N2 we don't know. So now you need to define what do you mean by basically 1 joule. Okay, so how you should basically define that thing. So in 1 joule, what are the things in the dimension it is there? M, L, T, these are the fundamental thing, you know. Now what you should do, see, for masses it should be 1 kg, and 1 kg is equal to 1000 gram, because you need to convert it to gram now, because if it is 1 kg here, it should be 1 gram in CGS. Length 1 meter, that is 100 centimeter CGS, na? Time, both of them are same. Now what you should do, you should compare both the side, because energy, unit of energy, you know, m L square T to the power minus 2, and that should be equal to this, m raised to the power A, L raised to the power B, T raised to the power C. Now you see one thing, here, how we can consider it is 1, it is 2, it is minus 2 over here. Okay, what you should do, see, if you see this thing in normally in this n1 into this mlt in this condition, what is the basic formula that we must maintain? Previously we know this n2, we making n2 as a uh, like no subject, n2 is equal to n1 into m1 by m2, like that. So that we must follow here, that we must follow in this case. N2 is equal to n1 into m1 by m2 raised to the power whole raised to the power a, l1 by l2 whole raised to the power b, t1 by t2 whole raised to the power c. Now what is your m1? See, this is your m1 in this case. M2, that is your m2. So you see, m1 1 kg, 1 kg means you should not write in kg because you should compare with gram now. So you write 1 kg means 1000 gram, and then m2 is 1 gram. Similarly, l1 100 centimeter, so l2 is 1 centimeter, and in time both of them are in 1 second. And then how basically you consider this a b c is 1, then 2 or minus 2 with the help of the dimensional formula of work done or energy, because this all joule and what is this, it is either energy or work done. So here in m you don't have anything, so you have only 1, don't have anything means you have 1, for l you have 2, and for t you have minus 2. So here a should be, because with the mass it should be 1, so that is why it is written 1. For b with the length it should be 2, for c with the time it should be minus 2. So that what we have written over here. Now so n2 should be n1 1 into this, so you can see it is, this is 10 to the power 3, this 10 this is what you can say, it is actually 10 to the power 2 raised to the power 2, so 10 to the power 4, and it is 1 raised to the power minus 2. So all together you will be having 10 to the power 7. Okay, so 1 joule is equal to 10 to the power 7 arg. Okay, now to convert 1 Newton into a system where mass is measured in milligram, okay, and length is kilometer, time in minute. So new system you need to discover. So Newton, or it is kg meter per second square, you know, because Newton is f is equal to ma, ma means m for kg, a means meter per second square, kg meter per second square is a unit of force in SI system. It is a unit of force in SI system, and whereas this mg, because the new system, kilometer and minute to the power minus 2, it is a new unit system, but we should maintain the that power, because here it is kg, it is given 1, mass m kg meter, it is given also 1, and second raised to the power minus 2. Here also you should give 1 minute raised to the power minus 2, because the structure should be maintained, because it is given force. Now force is actually having mlt to the power minus 2, so that structure, sorry, mlt to the power minus 2, so that structure should be followed, that structure should be followed. So that is why here I have given 1, here 1, here minus 2. Now what we should know, n1, let n1 Newton is equal to n2 mg km in meter. So the first thing, then n2 is equal to n1 of, first you make the table in the SI system, you write SI 1 kg, that is 10 to but here that was earlier it was gram, so 10 to the power 3 gram you have written, but here it is mg, milligram. So what you should write, so it should be 10 to the power 6 milligram, correct, because 10 to the power 3 into 10 to the power 3, Then 1 meter to kilometer, it is 1 by 1000, 10 to the minus 3. And 1 second to minute, actually it is given na, it is here it is given minute. Okay, so that has to be there. Now what you should do, that same thing, n2 is equal to n1 into m1 by m2 raised to the power a, l1 by l2 raised to the power b, t1 by t2 raised to the power c. Done. Then n2 you don't know, you need to find. N1 is 1, magnitude is 1 on 1 newton they have said na. Then m1 by m2 you do 10 to the power 6 by 1, and then l1 1 by 1000 divided by 1. And in that system, because why we should do this thing, because here in this minute inverse they are saying that is why second is converted 1 by 60 in that way. Okay, 1 minute is equal to 60 seconds, so 1 second is 1 by 60 minute, like that. Okay, so then what we should do, Mm, we basically place all the values over there, and then we need to basically simplify it. 10 to the power 6 raised to the power 1, 10 to the power minus 3 raised to the power 1, and 60, because 1 by 60 raised to the power minus 2 is nothing but 60 square. So it should have this value, 3.6 into 10 to the power 6 mg km minute raised to the power minus 2. So n2 value is 3.6 into 10 to the power 6. Now deducing the relation among the physical quantities, that is also there with the help of this uh, like this, dimensional analysis we can do. The method of dimensions can sometimes be used to get the relation between the other physical quantities that is not still established also. For this we should know the dependence, that means which one is directly proportional, which one is indirectly proportional, which one is dependent, which one is not dependent, which one is really linearly independent. In that case, suppose force with acceleration, it is directly proportional. Force with mass, it is directly proportional. If you don't know the relation, you cannot form the formula na. Example, consider a simple pendulum having a bob attached to a string that oscillate under the action of the force of gravity. Suppose that the period of oscillations of the simple pendulum depends on its length. Mass of the bob is m, acceleration due to the gravity is g. Derive the expression for its time period using method of dimension. What you should do? First, you should know what is the relation, dependency, how it depends. That means with the time period, they ask you na, derive expression for the time period. With the time period, what are the physical things like length, mass of bob, acceleration, how they basically vary, that you must understand. So the dependence of the time period on the quantities L, G and M can be written as initially like this. Linearly it is varying. Because we don't know the actual thing. Na? So first what we should consider, we consider all of them are linearly varying. Like what I consider the time, just a second. What I can consider in that case, okay, time, whatever the time is there, time period is directly proportional with the length, time period is directly proportional with the g, time period is directly proportional with the mass. Okay, that is what we are considering. Now you know one thing, if we write a combined equation it should be like this. Then if you write equal to, it should be a proportionality constant should be there. Okay, now how to define relation? See, initially time period is actually having in MLT conversion what is t, only t, and it is having a power, nothing is 1 only. K doesn't have anything. L length means m0, l1 and t0. Okay, Now here with this quantity, I should give a power, that is A. That means what I, because these are three different dependency na, with the L first I give assign a power A. Now with the G means what? Gravitational acceleration, m raised to the power 0, L t to the power minus 2. But that should have a power, that is B. And then, so we are assigning these powers, okay, don't worry about it. And G is done. And then M is only M is there, L is 0, T is 0, but we should assign another C. Now we should equate both the end. How do we equate? First we write T to the power 1, then K doesn't have anything, so don't worry about it. Write down here, it is having M0, L raised to the power A. 1 is there means L raised to the power A. Then T raised to the power 0. Then here M raised to the power 0. B, sorry, B is there. So L raised to the power B. L raised to the power B. T raised to the power minus 2B. Done. And another M raised to the power C. L raised to the power 0. T raised to the power 0. Now the thing is that, like the balancing of equation, you understand now, from with one element to the another element, you will do with one compound, not compound, one molecule with another molecule you are doing. Here first try to balance masses. Left hand side we don't have any mass, so 0. Right hand side we do have mass over here 0, plus, because powers na, powers we should do like that. And here also 0. And here we do have 1, that is C. So C is equal to 0. So what we can say? We can say C is equal to 0. C is equal to 0. Okay, 1 is done. C is equal to 0. Okay, that is done. Next, if you have if you consider length left hand side 0, right hand side L raised to the power A. So A, because power, with the power we are doing na, L actually having, so with this thing we have B plus 0. So A is equal to minus B. This is a relation, another relation. Another thing, you see, with the time you can do time, because left hand side time having 1 power 1. So 1 is equal to, right hand side this having 0. Here you have minus 2B, and here again 0. So 2B is equal to minus 1, B is equal to minus half. So therefore A is equal to only half. Okay. So what you can get from this? Okay, T is equal to, now you can understand, K is equal to, because M doesn't have anything, so M raised to the power 0. But you do have, dependency with this length. Okay, so length having, what is the dependency? Length having LB na, so minus half, and T actually having just a second. Yes, 2B, huh? Okay, sorry. Actually I have assigned, just a second. Actually I have assigned ABC for all these things now. For like length I have assigned A, for the G I have assigned B, and for the mass I have assigned C. So therefore, so I have not assigned individually, I have assigned for this them na, because L is this, G is this, and mass is this. So what I should write? T is equal to K, because L raised to the power A is half, so L raised to the power half. G raised to the power B is minus half. So G raised to the power minus half. And M raised to the power 0. So M raised to the power 0. So what you should write here, T is equal to K. Then this half minus half, you can do like this, na? L raised to the power half divided by G raised to the power uh, half. So it should be K whole raised to the power. So you can write square, it is square root, na? L by G. You can write like this. So in this way, you can basically deduce an expression or get an expression in that way. Okay. M doesn't have any, weightage over here. So you have only this thing. So that is what here also they have assumed something in this case. So what you can see in this case also, uh, they are also doing the same thing what I have done. You can remember my approach, the same thing. Okay. And then also whatever the value I was getting, see, they are also getting the same thing, K root over L by G. M doesn't have anything over here. Okay. So the funda is that first you look at the left hand side. Here left hand side time period was given. So time period is only T. And then right hand side, what are the dependent variables you have given except that of K? You just assign some values for that. Like L you give A, that means power, sorry. L you give A, then G you give B, and M is there, you give C. And then what you do, then you just write individual dimension for L, M, G, and then do the power, surge thing, that thing, equate both right hand side, left hand side, both the side. You do that calculation, and you will be getting the what I can say, relation for them. Okay. And K value is experimentally we got 2 pi. It is experimentally from other method we will be getting 2 pi. So the formula finally will become T is equal to 2 pi root over L by G. So that is the formula, actually established formula. But demerits of dimensional analysis. The dimensional analysis cannot be used in following cases. The value of the constant in an equation cannot be determined as that constant do not have dimensions. Only dimensional consistency uh, and not the physical consistency can be tested, because physically it is not viable. Correct. Dimensions can be found from the physical quantities, but physical quantities cannot be always guessed from the dimensional thing, because two or more quantities may have same dimension. Yes, we know na, work, energy, even we see moment, torque, those things are actually having same dimension. So how can you differentiate which one is moment, which one is torque? This is problem. The equation containing the dependency on more than three quantities cannot be determined using only MLT, because MLT is the basic thing. If you have more thing, if you have Kelvin, if you have ampere, if you have candela, all these things are there. Now you cannot do with the help of simple this dimensional analysis. Note that if four independent quantities are involved, then four variables, hence four simultaneous equations are required. Hence there must be four fundamental dimensions. The equation containing exponential, trigonometric, logarithmic function cannot be derived as they do not have dimension. The equation having relation other than product quotient cannot be derived. Okay, so here are the dimensional formula for some physical quantities. You can take the screenshot of it, or you can watch the video later on. End of the video you will be having this thing na. I'll be sharing this thing. These are the much more asked question from this chapter. So I have gathered all this thing in this table. Okay, this is also important. Actually I have given individually. See, this is for generals: length, mass, time, area, linear density, mass density, specific gravity, time period, frequency. Generally they can ask from each of them. Most probably from the specific gravity, relative density, time period, or frequency they can ask from this. Here from mechanics they most of them they are asking now most of the time impulse. Okay, force it is a normal thing. Then spring constant, force constant, spring constant, capital K. That is also many more times they have asked. Then work energy density, yes, energy density, pressure from gravitation, gravitational potential, universal gravitational constant, intensity of the gravitational field. These are repeatedly asked. Universal gravitational constant, repeatedly asked question. Then angle, this is okay. Angular frequency, angular momentum, moment of inertia, frequently asked. Angular momentum, angular frequency, moment of inertia, frequently asked. Bulk modulus, Poisson ratio, surface energy, surface tension, coefficient of viscosity. Bulk modulus, Poisson's ratio, surface tension, surface energy, coefficient of viscosity. Repeatedly asked. From heat, thermal capacity, specific heat capacity, and Joule constant. Repeatedly asked. Thermal capacity, specific heat capacity, Joule constant. Repeatedly asked. अच्छा, coefficient of linear expansion, Stefan constant, Boltzmann constant, and universal gas constant. Last का जो K, sigma and R, these are all important. K, sigma, R, Boltzmann constant, Stefan constant, universal gas constant. In electricity, uh, the permittivity of the free space, electrical capacitance, electrical resistance, repeatedly asked. Magnetism, magnetic flux, intensity of magnetic field, inductance, magnetic induction, repeatedly asked. In optics, refractive index, then luminance, that is lumen per meter square, decay constant, Planck constant, Wiens constant, repeatedly asked. So what actually you can understand, these are the important tables that I have made. So once you go through this video, at the end of the video, you just pause it and take just note down all these things. Okay, even if you listen to this video, if you listen to the lecture, you know I have mentioned the important from this table. What are the most important questions? I know frequently asked questions exactly uh, that you are going to have in your examination. Okay, so this is about today's lecture. Just wait a bit. Uh, uh, okay, so okay, you can leave this class now, and I'll be sharing the record.